You guys like open book, right? So this one, make it to be such that you need to open the book, answer the question. Let's go through it a little bit. How about that? Okay. Question 1. Equation 3.168 on page 110 of shorthand textbook give the closure relationship for calculating HLLS that is applicable for the inclination angle range from horizontal to upward vertical. Okay, 110, that's 110. 110, 3.168. 110, 3.168. This one, right? This one is Gomez et al. 2000. So this equation is from 0 to 90 degree. Okay. No question, of course. Equation 3.51 on page 72. 3.51 on page 72 of shorthand textbook give the criterion for transition B for horizontal and near horizontal flow. Yes, of course, this transition B, right? Like this. Okay. Equation 3.62 on page 73 is transition D.
Yeah.
Yes. It's okay if you write the dimensionless. It's okay. I didn't say whether dimensional or dimensionless. 62. I get this one. If you write 63, it's fine. But if you write 64, that is not fine. It's wrong. That is just the definition of T, but it's not the transition criterion. Okay, that's just the definition of T. If you have that, that doesn't tell you transition D.
What's about 53?
53. This one. What about this? It's transition C, right? But I asked for transition D, right?
Oh, I think I wrote this one.
Okay. So transition F for upward vertical flow, 4.22, page 142. So, because I have this as F, and that's a G. Okay. 4.23, 4.22, 4.23, 4.22. Oh, wait. 4.23 is for transition F, right? So, figure 4.22 on page 164, which is this one. 4.22 gives the graph plotted between delta tilde and xm0. Okay? If you don't know what is delta tilde or xm0, you cannot find that figure. Okay, so equation 4.74 and 4.75 on page 157. 4.74, 75. These two, right? What about other? Give the Wallace 1969 correlation for calculating entrainment fraction.
No, I mean this one.
Which one? Which number?
4.67.
4.67 is okay. 4.67 is capital I, right? Okay, that is 4.67. You mean this one, right? Is that the entrainment fraction? Entrainment fraction is F sub E, right? Capital I is the ratio between friction factor, right? So that's not entrainment fraction. You don't get penalty, okay? That's fine. So page 106, 3.155, this one. Okay, 3.155. Offshore Ham textbook give the formula to calculate the pressure drop of slug flow where Teitel and Bani 1990 model is reduced to the case of a uniform film thickness.
Yes, 108.
Okay, that's fine. No problem. No problem. It is the same thing. Okay, it's fine. So page 104. 1.44, 3144. That one. Okay. This one is to calculate pressure where the film thickness does not need to be uniform. That's an equation for calculate pressure drop where the film does not need to be uniform. Okay. If you put that equation here, it's wrong because in that case the film is uniform. If you put, Josh, what do you put? Okay. It's not that many, right?
What about?
But the rest you are fine. Yes.
102.
102. Which equation? Which equation number? What is equation number that you talk about?
3.136.
3.136 is that the equation to calculate pressure drop for the case that the film is not uniform?
Yes.
How do you get pressure drop?
So using this
This is a combined momentum equation.
I know,
It is
but using, so the
wrong,
one that-
zero.
No. The one that you're referring to.
Please explain.
Okay, let me explain.
How do
Let me
I?
explain.
You see this part, right?
Now let me explain.
To calculate the pressure drop of slug flow where the film thickness does not need to be uniform. So when you give me this, what do you do? How do you get pressure drop?
So
Where is the pressure drop in this equation? Where is the pressure drop in this equation?
but it's not.
It's somewhere that is.
Where is the delta P?
It's related to
It's inside of it, like.
Which is eventually it becomes this one, right?
Exactly. So
So
from
get
this,
zero. Get zero, okay?
No,
In the test you get -1.
no, from that.
So, Arya, you're a TA, right? If a student do this, what do you give? 1 or 0? Or 5?
If he has this same line of reasoning that I have,
What is your line of reasoning?
is that you get that same equation that you just said. Based on this.
How do you get delta P from this equation?
You got it.
So this is the indication that you read it briefly, not read it before the class, but maybe you read it during the class or during the exam time. Yeah. Do you think you deserve 0? Or it's not fair, totally unfair?
No, 1 is okay. I would say 0, but not this time.
Why? But how do you get delta P?
Integrate it.
Integrate what?
So let's put it this way. If
Integrate what?
you have a question,
Don't change the question. Don't change my question. My question is, how do you get delta P? How do you get delta P from this equation, Arya? Don't change my question. Please. Come on. This is a combined momentum equation, right? Eliminating pressure gradient from that and that, then you get this. This is after you eliminate it. So this, if you answer something like this one, you actually get more chance to say something. Okay, either this or this. Yeah, I may end up having to give you like, I don't want to, but maybe okay, 1 or something. But
Yes, yes.
This equation is after eliminating the pressure gradient term. So you don't stand a chance. Okay?
You better put it back there.
If you say this one, you don't even stand a chance. So
Yes, I didn't know.
how about 0?
0.
Is fair enough? Okay. And 145, show him textbook, give the criterion for transition H. 145. This one, right? 4.31. That is, give you the criterion for transition H. 140, give the criterion for the existence of bubble region. 140. This one, 4.15. Right? Okay. So this is to check if you do some, if you open the book or not. When you want to.
Okay, you could run Google search.
Or you have good speeding.
Google search. You know how to search.
Yes, totally.
Since this is the last class,
But this is not the last class. You have one on Monday.
before
We have in the syllabus. We have more. Yes, what's your request?
Can we talk about the exam before we leave today?
We don't talk about the exam this day. We talk about the exam on Monday.
Oh, exam is on Wednesday?
Exam is on Wednesday.
Professor, Monday is too late.
Monday.
Other classes too, right?
Is it this Wednesday or next week? It's next week.
Let's take a look at the syllabus. Okay. 30, 11, 1130. So next Wednesday is exam 4. Next Monday is the class time.
So no class on Wednesday, right?
We don't have. I'm not allowed to have class on this Wednesday. I want to, but
Oh, you want
I'm
to,
not.
right?
I'm not allowed to have any class on this Wednesday. So nothing on this Wednesday. See you again on next Monday.
So can we discuss
Yes,
exam 4
exam
today?
please.
I don't want to know. I want to cover my material. I will post the first page of the exam. How about that? Tomorrow. First page of the exam.
Instruction?
So the instruction. Basically it tells you that you have prerequisite. Okay. Prerequisite. Exam part. And you have that part, I think it's half penalty, and you have like something like this, part 2, I think, and you have a little bit of calculation, maybe just one question on part 3 or something.
Can you do like looking for question like this? Please.
Exam 4, what I can tell you is it's not that really comprehensive in the sense that it covers chapter 4 and 5. However, chapter 5 is about unified model, which is the model that valid for any angle. Give you a quick look, what is a unified model? For one of the good examples is this. Okay, quick look. For the unified model, the unified model valid at any angle. Okay, so one of the unified model use transition A. Transition A, which is the same as in the chapter 3. Okay, that is used in the unified model. That's valid for any angle. So when I said exam 4 covered just chapter 4 and 5, so chapter 5 already covered chapter 3. Okay, so you need to know everything.
Will it be the easiest exam?
If you bring the integration table, it should be easy enough. Do you know how to do basic integration? We have a little bit of integration and a little bit of taking the derivative, right, during our discussion in the class. For example, the transition that you remember this transition? This line, we take the derivative of the combined momentum equation and make it equal to 0. So you will have to know for sure how to do the taking the derivative. Differentiation, you need to know that. So of course, there will be a test to see if you can do that or not. And you should not worry about any of that if you know how to do that. If you don't know how to do that, bring your integration table. Integration table. Yeah. It's open book. Yes, Arya.
Yes.
Yeah, Arya.
Can I ask what's the flow pattern?
Flow pattern? What about it?
So we know the flow pattern in vertical flow, and we know the horizontal flow is minus and plus 10 degrees, right?
Okay.
What if you have a degree above?
Okay, all right. Let's start. He wants us to start. It is about this lecture. What do we do
I was
is...
saying because we need it in project.
Okay. So you read a book, or you do some... If you don't know how to do for any of that, you do some assumption as good as you can. You don't know, for example, you don't know how to do for 45 degree, right?
Yeah.
How do we do for 45 degree? Is it slab flow for 45 degree? So you don't know. You have to read a book a little bit. Or if you don't read a book, you may assume, okay, it's an average between horizontal and vertical or something. Have to do something. Alright, let's cover something. Now we will go through the model that valid for any angle. Please concentrate. Okay, look at this picture. On the left is for 1 inch, on the right is for 2 inch. Okay. STP, standard pressure temperature. VSL versus VST. So you will see that make the pipe bigger, the flow pattern map looks similar, right? So this part is SS. Yahweh, what is SS? Okay. Akin, what is SW? Modia, what is A? Okay. Then what is I?
In that section, elongated bubble, and the other one is not.
What is I?
Intermittent.
Okay, intermittent flow. Red one, what is dB? Disperse bubble flow. Okay, now when we increase the angle a little bit, that part kind of gone, right? The stratified region move somewhere, shift completely, and you see this square shape. That is stratified smooth, right? So when we increase the angle, I don't see stratified smooth. I have just stratified wavy. And that angle is just 0.25, not very much. Okay? Just 0.25, I cannot see stratified smooth anymore. Is this the case in the lab, Raymond? Do you see this? Or you don't see even stratified wavy?
I see stratified wavy.
You see stratified wavy. Do you see stratified smooth? Not really. Okay. So it's...
Would it be the human error just to have 0.25 degree in your lab? Not noticing it?
Oh, 0.25 degree. It is a very small number. It is very likely that there is a human error. How do we... But they didn't say about anything about that error.
I'm saying, for example, Brandon wants to see stratified smooth. So, do you get exactly...
Actually, we can see stratified smooth.
So when they do this, unless we have very long pipe, then small angle can be get from arctan of the horizontal length and the vertical part, right? So when we report any of this, especially for small angle, uncertainty analysis is needed. Okay, but within after the error analysis,
So
this is the case.
Does this suggest that stratified smooth flow pattern is the most unstable?
It's unstable when we have a little bit of angle. It's like all the way gone. So flow pattern is strongly dependent upon angle. 0.5. Okay, look at the difference between 0.25 and 0.5. Stratified wave kind of shrink. Okay. 1, shrink even more. Okay. 2, 3, or 2, 5, 10, 15, still there. 20, 30, gone completely. See, so when we increase the angle, stratified region shrink and eventually disappear. Okay, the largest flow pattern in the map is intermittent flow. Okay, dominant flow pattern for inclined flow, like in the book, or like in the book like this, right? So you have intermittent flow upward. Okay, 50 degree. Take a look at 50 degree. What do you see the difference between small and large pipe? You see this part? Raymond, which one is prone to have elongated bubble? Small pipe, right? If the pipe is small, we have like elongated bubble. When the pipe is big, we tend to have more slack. There's more more mixing at the same VSL, VSG. Because even though your mixture velocity is the same, but your Reynolds number is a lot, it's small, right? Reynolds number is rho VD mu. So when velocity is the same, bigger diameter it gives you more Reynolds number and more mixing. 70 degree. Take a look at this. See this part? No churn flow. 70 degrees, we have churn flow. And we have capital B. Arya, what is capital B? Bubble flow. It tends to have in large pipe or small pipe, bubble flow. Large or small? Large pipe. Yes. This one is 5.1. This one is 1 inch. Okay, 1 inch pipe. So we don't have bubble flow, but large pipe we have. Temitope. Why is that? Why do we not have bubble flow in small pipe? Which equation tells you the existence criterion for bubble flow region? You know that equation, right? Oh, we just talk about it, come on. We just talk about it. Transition E 4.15. I should fail you twice right when I answer it. 4.15. Tell me, Tope, how do we derive 4.15? Is a comparison between what and what? No, what was no? George, furthermore, how do we get 4.15? The existence criterion. We compare what and what?
Bubble velocity.
VTB, right?
Yeah.
0.55 square root GD and bubble rise velocity. So if your VTB is small, VTB is depend on square root GD, right? When diameter is small, VTB is small. So once you form the tail bubble moves slow and it blocks the pipe. Okay? If you remember, 4.15 is we get there by compare VTB and bubble rise velocity. So if VTB is slower, VTB is dependent upon square root GD. You remember that equation? Okay. So when it rises slow, it blocks the pipe. Any bubble coalesces with tailor bubble, and tailor bubble get bigger and bigger, right? If VTB is higher than bubble rise, whenever you form tailor bubble, it's just gone, right? It doesn't block the pipe. So that's what it is. After this class, you should be able to tell why that is. Okay. Right. So 80 and 85 we have churn flow. 90 we have churn flow. So let's take a look at 50 and 30. 50 and 30, we don't have chain flow. They don't observe chain flow. Okay? There's no chain flow. Horizontal, there's no chain flow. Okay? And we are going to give the reason for that. Okay, soon. So chain flow is between like 80, 85, 90, that's chain flow. Okay? Right. The reason for chain flow to not appear in the lower angle is going to explain later. Okay, basically it's about the buoyancy and the stability of it. So now if you see the flow pattern map, at least you should be able to tell whether it's upward flow or horizontal, right? If you see chain flow, obviously is if it is air and water, if it is air and water 2-inch pipe or 1-inch pipe, if you see chain flow, it is not 30-degree upward. Okay. Alright, now let's take a look at zero. Zero look like this, right? If we go a little bit downward flow, -1, you can see that intermittent flow region shrink a lot. Okay, and certified wavy kind of go on top of stratified smooth. Happen at like higher VSL. So this -1 degree, -5 degree for small pipe diameter, stratified smooth is just gone. We have just stratified wavy, right? See this? So -10, stratified smooth, gone forever. No stratified smooth anymore. So naturally, so what is the force? What are the forces that we do the comparison to get certified wavy region? When they derive it based on which forces? That is transition A, right? It's not transition C. What about transition C? How do we derive it? Go to the book, go to the book. How do we get transition C? Equation that Maya answered. Yeah, remember that, Maya? That transition C. So transition C is comparison between what and what? And wave growing criterion, right? It is a wave growing criterion from what? Jeffrey. So it's just that one equation. In addition to that, we have transition K. Transition K is based on the idea that Fromm number is more than a certain value. Is it 1.5 or something? Yeah, more than 1.5. So this means the gravity itself make the liquid layer to be unstable and form the wave. Okay, so the gas flow rate may not need to be enough to create the wave, but gravity itself is enough to make the wave when we flowing down.
What is the general rule if you increase the density of gas a lot? What's happening?
You tell me. What is your idea, my dear PhD student? When we increase the density of gas a lot, then what do you think happened? This is in one of the homework, is it? Yes. I remember. Oh, it's not in the project, it's in the homework. Very first homework, I asked you to use the flow pattern map and change gas density. So let's say we change the gas density to become water density. What do you think? Become single phase flow, right? Kind of single phase flow. So go do it. I actually don't know now. Okay, that's why I asked for your idea, because I don't know. Okay, but I can guess. Okay, if gas density kind of going up, we may have like heavier gas even we go downward. So if gas density is the same as water density, so there's no buoyancy force. When you flow a little bit, it's kind of mixed, right? So maybe we can have just this bubble flow if the density are equal, like two liquid flow together. Okay, minus 50. Alright, the part that I want you to concentrate is this. You know that when we move down, stratified wavy region go up, right? It enlarge. Not only that. Look at intermittent flow. Intermittent flow region kind of gone for 30, right? So 5 minus 1 is this, right? And then it shrink, and then it shrink further, minus 30. Look at minus 50. Look at this part. Somehow, annular flow kind of move over stratified wavy a little bit. Okay, this minus 50. Minus 70, okay, annular flow happen there. Minus 80, how about that? We have more annular flow. Minus 90, falling film. We don't have stratified wavy anymore. Stratified wavy is gone for minus 90. Okay, so minus 90, you have annular flow. Kind of falling film, okay, for minus 90. You probably don't have any entrainment, okay, and you have intermittent flow and this bubble flow, no stratified flow anymore. So if I show you this graph and tell you that it's for 1 inch and water, you should be able to tell right away that this is minus 90 because it's so unique, right? Because it doesn't have stratified wavy anymore. Okay, you cannot have stratified wavy when you go 90 degrees downward, right? There cannot be separation on one side of the pipe. In the book, there's a discussion that that thing can happen, but it's not quite realistic. It's depending on the inlet condition. If we start with flowing water in the middle, we can have water in the core, but that's not what they observe in the field. Okay. So after we know all the flow pattern, the next step is we should come up with a model that can predict for any flow pattern. Alright, so Shoham, 1982, we discussed it by, okay, first consider the upper flow. So stratified smooth flow pattern appear as delta greater than 0.25. We have seen that, right? And you have seen that this flow pattern is insensitive to the inclination angle. You remember transition F and G? It looks the same. This 50, right? 70, 80, 90, it looks the same. So this is 10, this is 5. So the transition to the this bubble flow is not really sensitive to angle. Okay.
Professor, to answer the question I asked, if you increase the density of gas,
To answer the answer you asked, please continue after class. Okay. Please come to see me in my office hour.
I have the answer, that's what I'm saying.
Okay. What's your answer?
So you have more probability to get into slot flow.
More slab flow.
Yes.
Okay, thank you for your answer. Let's move on. For upper incline flow, for 0 to 10, we can use Tycho-Doppler model. No problem. Okay. For angle more than 10, we need to use a modified upward vertical flow. And part of that, we need to know bubble to slab transition E. So transition E is modified by adding sine theta. Add the sine theta into it. So we have this part. And the existence criterion stay the same, doesn't have sine theta. Just that, and it works. Okay, just that. So this can use for 70 degree, 80 degree, or whenever you have bubble flow. Okay, easy enough, right? Just add sine theta. Transition F. That's sine theta.
So when you say bubble flow, does PVC bubble flow with that disperse or stop? The bubbles also look like disperse bubbles as well.
You didn't look at the, yeah, it's difficult to tell, but the closest bubble flow is to look in the fish tank upstairs. That's a bubble flow. That's what I have to show you. In the lab, it's difficult to have bubble flow, even in second floor lab. Transition F, okay, combination between turbulent force and surface tension, that's transition F, right? Transition G is void fraction cannot be more than 0.52. These transitions are not a function of angle, therefore, no E, okay. For this upward inclined flow, use F and G as before. And I found later that the equation that I showed to you is not the same as in the book, but that is typo. We should use the one in the book form, okay? So, transition F and G, they are good already, can work from 0 to 90. Okay. This is the chapter that tell you that. When you have F, you have G, you can use that all the way from 0 to 90. Okay. Transition J and H. Transition J, previously you used this, right? Turner equation. And if you want to do it, add G sin theta, that will be unified transition J. But I have to show you a better version of that, right? That graph from Bunny model. This one. Remember this? This is truly unified model. Annular flow over here. Use this one will be even better than add sin theta to Turner equation. Okay. Turner equation give you what? Let's go back. You see this straight line? That Turner equation. You don't want a straight line, right? So if you use Turner equation with sin theta, you get that. You get that. It's not real, right? You don't get the curve. You don't get the curve like that. But Bunny model give you the curve, not just a straight line in flow pattern map. Okay. So, okay, churn flow. So basically they suggest you to use sin theta, add G sin theta in it, and it's done. Okay. But the one that we talked about earlier is a better version. Okay. So the book suggests consider the churn flow as a part of intermittent flow. That's the suggestion in the book. And it said, okay, below 70 degrees churn flow disappear. Or even if it's appear, they do the pressure drop calculation as if it is the slug flow. That's the suggestion in the book. Downward flow pattern for downward flow. So for downward flow, transition A is fine. Okay. For theta less than -10, transition A is terminated by the transition boundary to this bubble flow. Transition A is actually good already for downward flow, but it gets truncated by other transition. Alright? So below 70, it terminated by falling film transition boundary, and we will look at other transition. Transition B, intermittent to another flow. This one, right? So this transition B is valid when the stratified flow is unstable. So you check transition A before check transition B, right? So it said 70 and 90, transition B can continue to very low gas flow rate, anything. So this is the version before unified form of Bunny model. If you already know Bunny model, use that graph. You remember this graph? Use this one between X and Y. That's a truly unified model. Okay. Transition F and G valid for downward flow too, because they are inclination angle independent. So for downward flow, F and G is still good. But later on, I will show you a better version of transition F. Transition F can be better. When you do the homework, you may realize that, homework 7, right? When you do transition F, it is not the same as what is given. Okay. But if you do the method in chapter 5, it will be identical.
Okay, alright, now let's discuss about it. Let me share the pattern here too.